Ooh, that would be bad.
Oh, no, we're live. Okay.
We think we're live?
Yes, we're live.
Eight, isn't it?
It is. Only 4 people around, though. 5.
There's only 5 people.
It's okay.
Good morning, everyone. It's 8 o'clock. Ryan tells me there are 5 viewers on the live stream. So wake up, everyone. We'll give you a few seconds. We had some trouble actually starting the live stream. So hopefully if you stop and rejoin, you can mention that in the Zoom if you want to go live in the Zoom, Melissa, and just say.
I did.
Okay.
Hi, we are live on the live stream. Please refresh your YouTube page and you will be able to find
Are you able to see the live stream?
it. You can't see the live stream either online. It's, it's telling me that it's live, but it's not showing me where the live stream is. It's not showing me the live stream either. Sometimes it takes a minute. Like it's telling me it's live.
Mm-hmm.
But I don't see it. They're 15 now, so clearly people are finding it. I think the live stream is just taking a little bit of time to load for everyone. So just give or take a few minutes. Also, someone is unmuted and is having a personal conversation. So if you don't want us to hear it, please mute yourself.
Those are the cute pictures I sent you yesterday.
Yeah.
Oops, we're having a personal conversation. Am I muted?
Let's also let's chat with you. Melissa. Yes. I texted you from Mark's computer the link to the live stream, so you can put it in the Zoom chat to help people. Got it. Thank you so much.
Do you see it streaming here yet?
No, I don't. Which is
If you can't join it, that's I'll just say this.
Okay, I sent it to them. Thank you so much.
Hi everyone, we're trying to verify that the live stream is working. So if you're hearing me, can you unmute me? Am I muted? So if you're hearing me, great. And the reason I'm wandering around the room is we're trying to make sure everybody can see it. Melissa, are you able to view the live stream?
I am able to view the live stream.
And
There are 60 people on.
And Ryan, but you can't see it from your end yet?
No, but I don't understand the internet.
We can take a quick
Found it.
poll. Okay, guys. Good morning. Happy Wednesday. Is it Wednesday? Oh, welcome back. I wanted to start right here today where we left off. There was a question right at the end, and I think I misinterpreted the question, and I might have made this sound confusing. So there was a question I don't remember exactly what it is, but let me say what I think the question was, and that is, if energy leaves the system as heat, does the surroundings absorb all that heat? And the answer is yes. In this class, if I say the metal is the system and the water is the surroundings, then heat that leaves, energy that leaves the metal as heat, so that's a Q, that all goes to the surroundings. So that's kind of what this is saying right here, that the magnitude of the heat, the energy leaving the metal, is absorbed by the water. So the general statement is that the energy change for the system is equal in magnitude to the energy change of the surroundings. So those two things are always equal, but you can't always say that a heat change between those two is the same. But let me just clarify, if there's an arrow and it says heat's flowing from the system to the surroundings, then yeah, every single joule that's leaving the system ends up in the surroundings. And if heat is being absorbed, so energy is flowing in as heat, every joule makes the transfer. What happens after that is what might cause these things, the Q equal Q, to not be the same as the E equal E. But when the heat's flowing, and this is the only thing that was happening there, so heat flows out of the system into the surroundings, joule for joule. So Q of the metal, the system, Q of the water, the surroundings, that's absolutely fine. That's all that's going on. Heat flows out joule per joule. So we can go, oh, I don't have to go on. We can go on right from here. So here's where we get into the fact that there's another thing that can happen when energy changes. So we do have to keep track of other things besides heat. And heat we associated with random motion, the random motions of the particles in the system. That's associated with temperature. So temperature and motion of particles are directly correlated, and heat, random motion of particles, transferring from one system to a surroundings by the random motion of molecules or particles, that is heat. But you can do things in a concerted way rather than having all the particles move in random directions. If they all move in the same direction, boom, that is different. That's a positional change. And if you change position, you're doing work. And that's another form of energy change. And we make that firm differentiation between the two. Work is all the particles in the system working together. Heat is random. No, the particles aren't working together at all. The energy can still be transferred, but it has to be transferred in kind of a random way. Oh, I bumped some of us bumped into you, so you'll get a little bit of energy. But over here, we're not bumping into each other. So we have this energy, potential, and work. There's energy associated with the position of particles, and you already know this. I'm sure if I I have to grab just the pink part. So if I were to draw a hill and have a little ball at the bottom and compare the energy of the ball at the bottom of the hill with a ball I push up to the top of the hill. So I did work to go from the bottom of the hill to the top of the hill. And by doing that work, I gave the ball some energy. What kind of energy? A positional energy. It's the position of the ball relative to the surface of the earth changed. There was a positional change here. We can call it delta H, the height above the earth. And that's proportional to the energy change of the ball. That's a potential energy. And it's interesting, we call it potential. I can give my body some potential energy. If I step up here, I have, I go out of the frame, but I have more potential energy than I did down here. I could display that. I could put a soda can on the ground. One way I could crush the soda can is just step on it. And the crushed can, I put one soda can crush worth of energy into it. So our unit of energy could be soda cans. 1 unit of crushing, I can do that straight away, directly put the energy into it. But I could also step up here and then jump down and crush it. Both ended up crushing the can. But if I put the energy into my body first and then crush the can, that was a 2-step process. When I put the energy into me, I now have the potential to crush the can. I have potential energy. I can potentially crush the can. I don't have to crush the can, but if I want to crush the can, I have the potential energy to do it by coming down the hill. So I can release my potential energy. I can gain potential energy. To gain it, I can't gain it through absorbing heat. I have to gain it by having work done. So this change in energy is going to be proportional to some work done on the system. We'll give that the symbol W. And that work done on the system, just like heat, is a transfer of energy. So work is going to have the units of joules again, but it represents a transfer of energy between the system and the surroundings. So if you're the person who pushes the ball to the top of the hill, that energy came from you, from your legs, from your burning of your energy, transferred into the ball at the top, and you'd take your body to the top too. So you gave your body some potential energy as well. So let's look at that. I guess I'm already here. I think all I have to do is stop my annotate. So let's look at another system. So here's a system, and I'm going to bring, in this case, rather than a ball, I'm going to bring in some charged particles into the system. So my system are these 2 charged particles, a plus charge and a minus charge. And we'll just give them 1 positive and 1 negative charge. So they could be a proton and an electron. Protons have +1 charge, electrons have -1 charge. Could be what the particles are. The actual charge doesn't matter. I'm just saying they're the same positive and negative charge. So if that's my system, how is the energy stored in that system? Well, remember when we said heat, the energy was stored in the random motions of the molecules. Here it's stored in the position, the relative position of those two particles, because the positive particle and a negative particle attract each other. You probably know that. Positives and negatives attract. So there's an attractive force between those two. Just like the force of gravity between me and the earth. I have to lift myself up. I have to work against that force to give myself some energy. Same thing here. If I pull those charges apart, I'm going to do some work. So let's say they're at this distance, R1, and I pull them apart. I have to apply a force to each of them, and that force pulls them apart. As a force moves through a distance, so you apply a force over a distance, that's one definition of work, force times distance. So by doing that, work was done, in this case, on the system. We're going to measure that work in joules. The distance R2 now is bigger than R1. The particles are farther apart. So I really have two states that I can think about. The first state, they were close together. The second state, they were farther apart. So there was a change, and I can think about the delta E for that change. How did the energy change going from close together to far apart? So let's look at it this way. Let's say this was my system initially close together. This is my system final far apart. What is the energy difference between those two? So let's talk about that in terms of a chem quiz. So the plot of the potential energy of the two charge system, plus and minus, here I've made them electrons, a plus electron and a minus electron. How does that look versus the separation R? So I have energy plotted on the y-axis, the separation along the x-axis. The relative energy is the product of the charges times divided by the distance between them. So how does that energy change with position? So think about that for a minute. Ryan will start the clicker, the iClicker system, and you can take a vote. So let me know when you're ready, Ryan, and you have the group of 4. Hopefully you're still shared.
Hi, please join your breakout rooms that you've been assigned
to. I guess if we show this. About how many people are in the Zoom?
That's a good question. I don't know.
Is it easy to tell?
No, it's not easy to tell because everybody's in breakout rooms.
That's okay. Yeah. I'm just wondering how many responses we should expect.
Each breakout room has 6 people, and there are 20 breakout rooms, so 120.
Oh, fantastic. Okay, so this is your initial thought. If you haven't voted yet, go ahead, take a stab. And I'm interested to see what you voted. So Ryan, of these 100 responses, let's see what they look like. Did that freeze? So we are kind of equally distributed between A and then the rest of us think B and C. So let's open it up. Talk to your neighbor, talk to your people that you're sitting with in your breakout rooms. See if you can come up with the answer. And I encourage you. This has to be a little foreign. We throw you into these breakout rooms, and you've never seen the other people in there. Maybe you don't see them at all because their video isn't even on, and you're looking at a big M or something. So I encourage you. You don't have to turn your videos on if you don't want to. It's early in the morning. Maybe you're still in bed, but talk to the people. Turn your microphones on at this point and say something like, "I thought it was A. What did you think?" You saw that Ryan sent out an announcement where we're going to allow you to choose the people you are in your breakout room with. And we're starting to do that process today. You can respond to the form that was in that announcement if you want to choose who's in your breakout room. That'll make it easier to chat. We certainly want you to talk with your friends. If you actually have friends, put them on that list, and you can chat in the breakout rooms. I'm going to shut up and let you chat. Can you mute me? I have audio. Can you hear me in the live stream? Do I really have audio? I just want to make sure I didn't.
You guys to use the equation that's on the slide.
Let's see if I'm.
So the equation that's energy is about over the radius or the distance between them. So if if the distance increases in the denominator, then your energy would actually decrease. So think about that. And I'm going to go to a different breakout room.
Okay. Let's push your buttons if you haven't so far. I heard a lot of good discussion about this. I'm going to try to join breakout rooms. We're going to try and get my equipment set up so I can pop in and talk to you personally in a breakout room. But go ahead, push your clicker if you have not so far, and we'll see what you're thinking. We've got about the right number of responses. So Ryan, let's see what they're thinking. A was initially quite popular. Now A and B are equally popular. So let's talk about it. We'll go back to control here. So what's going on? The energy is proportional to the product of the charges over the distance. So what that means is we can say the product of the charges over the distance. The charges have opposite signs. So it's going to be E times E. We'll have about, there's a little factor missing in there, but it's going to be about -1 times a constant over R. So minus a constant over R is how the energy is going to go. So the energy will have a -1 over R plot. The -1 over R plot is this one. So this is how the energy changes as a function of position. So the position short here, we have low negative energy. As you go in separate in R, the energy increases towards 0. Now, this whole idea of energy increasing towards 0 is a little disturbing when you first hear it, I think. So the highest energy is when they're furthest apart, but that energy is approaching 0. So one of the reasons, there's a couple ways to think about this. Energy is a state function, only depends on the initial and final state. One good thing about that kind of system is you can pick then arbitrarily where 0 is. If it's just changes you're talking about, you can say, well, the 0 in energy, you could put the 0 in energy at the top, the highest energy level. You could put the 0 in energy at the bottom. If you put it at the top, then all your energies are negative. If you put 0 at the bottom, all your energies are positive. But all those are just energy changes. So you can slap 0 where it's convenient. You could put 0 in the middle of the two. And usually we pick somewhere convenient. So for particles, we say the 0 in energy, let's just say that that's when they're as far apart as possible. We'll call that 0, and we'll measure everything relative to that. So that kind of looks something like this. Let's look at just that plot. And with just that plot, you have the energy increasing with R. It's increasing from a negative number, big negative number, to a small negative number towards 0. And the 0 is the largest energy because all the other energies are negative. And we can say you reach that when you get an infinitely large separation. So the idea of 0 being the biggest is something we just have to accept because we set 0 as the top of our scale. We're allowed to do that, put 0 wherever we want. So in this case, the particles, when they're far apart, have the higher energy. When they're close together, they have the lower energy. So here's the lower energy system here. The initial system, let's say, that's where the system started. We pulled them apart and they went to a higher energy. This higher energy just happens to be where we're putting 0 of energy. So, like I said, if I wanted, I could have put energy down here. How's my eraser work? Think. I could have put 0 down here. But it's just a choice we make, and we make the choice as a group, as physicists sometimes. Let's say, okay, everybody, let's put 0 as the particles far apart. That's our reference point. Is there a question?
What does it mean to have negative energy?
So the sign of the energy is relative to other things. So energy changes can be negative. So what we're gonna worry about, let me put my energy back at the top when it's 0 here. Well, pooh. Maybe I probably have to do that. If I put this at 0, then they'll have a, this will be a negative energy relative to this one. So again, the term negative energy, can I have negative energy? No. My energy is negative relative to this one. My energy is just lower than that one. So we put the negative sign indicating that you're lower than this one. So relative positioning is where a negative would come in. Again, a direction going up or down the energy scale. This is an up, a positive delta E. This is down, negative delta E. And the relative ordering is where you'd see a negative sign reminding you that energy is lower than another energy. So if we continue then and say, well, this process going from close to far was an increase in energy. We started out relatively low. And since we put 0 up here, relatively low, we would have classified as negative. We go up towards 0. Our energy change is positive. Another way to think about that is, what did you do to get from here to here? Imagine it was a spring and the particles are connected by a spring and you pulled them apart. Now, I think you probably intuitively understand, if I pull them apart, I'm doing work on the system. My energy is going into the system to pull them apart. So if energy is going in, then that means that system is going up in energy. So we have work going in, supplied by me, the surroundings. I put work in, some of my energy as work, to lift the system up. Pull, put energy in. So that's the expression we see here, and that's one way to, that's a good way to think about how did the energy change? Well, work went into the system. So the energy change, again, is initial minus final. And in this case, that is greater than 0. Energy went into the system, and that's equal to the work that we did. So you can say work and entered the system. I'll give that positive sign. And again, that's just a direction. It's saying the work went in. We're saying whenever energy enters a system, we give it the positive sign, because that energy entering the system tends to raise its energy. Energy's entering as work, that energy raises in the system. Same thing we did with heat. When heat came in, when energy came in as heat, we gave that Q a positive sign, because that raised the energy of the system. So here it is. We'll summarize then. Work coming in, whoever it was that pulled the particles apart was in the surroundings. Pulling the particles apart, work came in that raised the energy of the system. And in this case, the energy of the system goes up. It's equal to the magnitude of the work. And that is a positive number. The energy came in. We gave work a positive number. In this case, though, the temperature did not have to change. Every joule coming in changed the position of the particles in an organized way. So there's no additional random motion in the system would have caused the temperature to change. So we have a very subtle point here. Energy can enter a system and not change its temperature. If energy comes in as heat, changes the random motions, then energy goes up and the temperature goes up as well, because the temperature measures those random motions. I can have energy come in as work. All the random motions stay the same, but relative positions change. So I can still have that relative random motion, but positionally things change. Their temperature can be the same with more potential energy. Question?
2, actually. So potential energy is to work as temperature is to heat?
The question is, potential energy is to work as temperature is to heat. Shoot, I don't think I would make that exact correlation, because if you want to correlate heat and temperature, you have to be very, very careful. What you can correlate is energy of the system is related to its temperature. So we can definitely say work changes the potential energy, heat changes the energy of the system. Work and heat can both come in and change the energy. A temperature change is related to that energy change. We could have got that from the heat coming in. In that case, you could say, oh, that's directly related to a temperature change. We're going to find, though, that heat can come in without changing the temperature, because the system can keep doing things. So you can correlate heat coming in with an energy change, but the temperature change is related to the total energy. The total energy might change for some other reason, and the temperature might not change. In general, if nothing else is going on, though, I think you're exactly right. If heat goes in, you'll encounter a temperature change if you don't allow anything else to happen. So that correlation is true in that isolated case. Heat flow, but nothing else can happen. So let's continue. Let's just do our analogy of, there was another question, Ryan, were those related?
The other one was answered.
So the system has high energy, so the system can do work on the surroundings now. So the system, just like the spring, could come back together and do work on the surroundings. So if the system does work, that's work that exits, that's energy that exits the system as work. And of course, that would have the opposite sign. We'd call that negative work. But again, the temperature does not have to change. So we see a system. Let me see if I can give you another system you might know about. So let's say you have the piston in an engine, and the piston moves and it makes the engine turn. So that system is doing work outside. Push, and I do some work. So that's a situation where you have the system doing work on the surroundings. Now, as the system does work on the surroundings, that piston will recycle and it will come back. And as it comes back, essentially the surrounding is doing a little bit of work on the system, but you do something clever. You put heat into the system so it can convert that to work and give it back to the surroundings. So that could happen without the temperature changing. So consider this. The system comes together, you let heat come in, but every joule of heat that comes in, you let the system do work on the surroundings. A joule of heat comes in from the surroundings, you do a joule of work. Get a joule of heat in, you do a joule of work. Get a joule of heat in, you do another joule of work. All through that, the temperature would stay the same because heat's coming in, but you're doing a joule of work every time that happens. So those things are related to each other, and we'll see that now a little more. Still, the energy is conserved. So, summarize. This always is the case. Energy of the system is equal in magnitude to the energy change of the surroundings. Put a minus sign on there to indicate the relative energies. So if it were heat coming in, we're going to give that heat Q a positive side if it comes in. We're going to give heat Q a negative sign if it's energy going out. And remember, that's just energy flow in the form of heat. Energy flow in the form of heat. Energy and work are the flow of energy. Energy and heat are the flow of energy. So in this case, if we have some heat leaving the system, that would cause a change in the random motion of the particles outside, and those the temperature of the outside would increase. We'd increase random motions. We would get more kinetic energy outside in the surroundings. So we have a correlation between kinetic energy of the particles increasing in a random way. Kinetic energy is dependent on which way you're going. So kinetic energy of the total system increases because the motion of every little particle can increase. We can do the same thing with work. So work, I can put energy into the system with work, and now the particles all have to move in the same direction. Can't be random anymore. I got to push. So work can enter the system, and if energy enters as work, that's a positive sign for work. If the system does work, then that's a negative sign for the work. So now we're talking about a system where I'm going to have work done on the system. All the particles go oomph, and that's what happens in your piston. in your engine. All the particles have a concerted motion in one direction on average, and that's able to do work. So we're talking about work in this case being done on the system. There was uniform motion in the system. So we can summarize that then, and this is why I was being very careful earlier about equating energy in the system and the surroundings and the heat flow, because this is the general expression of energy change. Energies change in the system or the surroundings via the flow of energy through heat and work. Heat and work are the flow of energy. We keep track of both of them. Both of them contribute to energy changes. And they do it in these subtly different ways. Energy change comes from heat, either energy leaving or entering as heat, or work, using energy to do work, or work being done on the system. Keep track of both of them, and you'll know the energy change in the system. So both of these are kind of statements of the first law of thermodynamics. If the energy change happens in a system, it's add up all the heat flow and all the work, and you'll find the energy change of the system. So isolated systems can't change their energy unless there's flow of energy in heat or work. Those things are coming from the surroundings or going to the surroundings. They're just a flow. Okay, we're going to associate potential energy with position. We talked about position, height over the Earth, or charges being separated. If there's an attraction involved, then you have to do uniform motion work to separate them. That could be charged particles. It could be the particles on either end of the spring. It can be me versus the Earth. All those are attractive energies, and positionally, if you change their position, you get a different energy. To change positional energy, you've got to do work. Oh goodness, so here, I hope you guys brought your rubber band. We've been telling you for a couple days to bring a rubber band. So let's talk about it. A stretched rubber band is suddenly released. What happens to the temperature of the rubber band? Increase, decrease, or stay the same? Ryan will start a poll and we'll look at that one. Well, this one ended up with a number. So Ryan, you got the poll started and I can go back to the group of 4. We're really going to have to figure this out. If I touch this, you can add, right? Oh, you still have to do the number no matter what. Oh, darn it. You got to do a better way to do that. While you're opening that, I'll just go back to the picture.
My thought is that I think that you should just put the slide of 4 after each Chem Quiz.
So I can switch to it. That's not a bad idea. Yeah, if you have presenter mode, you can just pick it and say, go back to that one. Are you in a situation where I can switch to you now? Are you re-shared? Okay, we already have 104 responses. Apologize again. What Ryan and I are trying to do is figure out how to let you look at in the live stream all the slides together. So you see all the information you need. Your iClicker captures the Chem Quiz. You have that one in front of you. We want to show you all of this in case you need it, and I think you could use it. So here's the idea. We have a pretty broad distribution again. About half of us think A. So Ryan, you can stop that. I'm going to take the share away from you anyway. So a lot of you think the temperature is going to increase on that rubber band after you release it. So talk about that in your small groups. And I may be able to join a group this time. Can you mute me on this, Ryan? And I'll just use the Hey, I'm back. I jumped into a breakout room. I hope all of you in breakout rooms as we go. That was kind of fun talking with Rocky and Marshall and Alyssa. It's hard for me to read all the little tiny names. I'm looking at my iPad, so they get really tiny. But thanks for talking, guys. That was fun. Go ahead, enter your vote if you haven't so far. Let's get about 100 of you and we'll look at the result. You can change your vote, right? If you till the last minute, yeah. Okay, there's around 100 of you, Ryan. Let's see what people are thinking now. A, still quite popular. B and C, not as popular. So let's do this. How many people, I hope some of you brought a rubber band because we're going to do the experiment. So Ryan, I'll take over again. I'll come to center screen here and I'll walk you through this. If you have your rubber band, play along. So take your rubber band, stretch it, and hold it. So you see how I have it stretched and I've held it? Now, touch the rubber band without releasing it, touch it to your bottom lip. That's just your thermometer. Bottom lip, bottom lip, bottom lip. Get an idea of the temperature. Now, we're going to do the chem quiz. A stretched rubber band is suddenly released. Release it, touch it to your lip again. Let's vote one more time. Can I share? Okay, you should be able to vote this fast this time. If you had the rubber band, the answer is obvious. So we'll be able to kind of chuckle at the people. In fact, this poll will be a measure of how many people had a rubber band. So we'll get about 100 of you, and not everybody had a rubber band, but you see, at least on in the majority, we've changed to C. The temperature of the rubber band measurably decreases. It gets quite cool when you touch it to your lips after releasing it. You have to hold it long enough for it to come to equilibrium with the room, then release it, and it's quite a bit cooler. Why is that? Oh, people are beginning to agree with me. Are you doing the experiment or are you just listening in? Apparently you trust me either way. Let's go to the PowerPoint. So what happened there? Now, you put energy into the system when you stretched the rubber band. So you gave the system some positional energy, some potential energy. It's the energy stored in the stretched molecules of the rubber band. Now, when the rubber band comes back together, it's doing work on your hands. It's pulling your hands back together. And if it pulls your hands back together, the rubber band, the system has to do work. Well, how can the system do work? Well, it's got some energy. So it has to use some of its energy to do that work. So the system uses its energy to do work. Work flows out, energy flows out. Now the total system energy has changed, and you can recognize that as a temperature drop. So the system used some of its internal energy, and you recognize that it used some of its energy because now it's at a lower temperature. Temperature is a measure, relative measure of the overall energy of the system. It's a measure of energy content, total energy content. So I had a high energy state. I went to a low energy state. So I did work. So there was no time for heat to flow in or out. So the system used its own internal energy, and we saw that it used its own internal energy because its temperature went down. This brings up a general point, and the general point is heat takes time to flow. Work you can do right away, but heat, you've got to wait for the heat to catch up. Heat's always lagging behind because heat is just random motions and they have to communicate with each other. You can do work fast, and you saw that heat takes some time to flow. So you stretch the rubber band, energy went in, you would probably notice a temperature increase a bit. But then if you wait a few seconds, it's the same temperature you started at because you that energy had time to leave the system. So the heat flow just lagging behind the work energy flow. So in this case, you saw it happen on your lip, I hope. The answer is the system does work. And I've related the change in energy to the change in temperature. I got some words up there that you don't have to know. I'm sorry, I pulled this Chem Quiz out and I forgot to change it exactly for this lecture. You can tell it's numbered. Forgive me, going fast. You don't have to know these words up here, adiabatic. This expression for work, don't gotta know. All you have to know is the system had to do work, and because it had to do work, it had to use some of its energy, and because it had to use some of its energy, its temperature went down. Okay, so I'm going to change lectures. Everybody, you can take a short break. I'm just going to load up the next PowerPoint. Hopefully that's a straightforward thing to do.
It should be just on the next.
I didn't attach it.
I think you did.
No way.
I think you did.
Ryan says I did a smart thing and I attached it. No way. No, I didn't.
No, you did.
Well, let me do this. If I attached it, I should just be able to stop the show and just go to it. Oh my God, I did. Okay. Is that the order I want to do them? Oh shoot, they are there, but they're not exactly right. You guys are still taking a break. I'm gonna open another. The best way to do that, I think, is go to the locker, go to the files, go to the drive, go hopefully to Chem Summer, go to 4. Oh God, that's all we need. So this is just frustrating as heck.
It's not even recently open?
I hadn't opened it yet. We actually can get through some of it because some of it is correct back there. I want to go back a step. How do I go back from recent to back one?
Why don't you just click on the amounts of energy one that's right there? It's the
Yeah. We could run it from. Oh no, we can't run from yours either.
You can run it from mine.
But yours has the same one I do. I can go to. I could try to get it off box. That would be really crazy. Does that have a prayer of working? Yep, this is the way I wanted to do it. So you won't have the group of 4. But let's start. Okay, can you bring me back live? Hey guys, sorry for that brief interlude. The device here has just a lot of great properties, but the whole file system and getting PowerPoint to open the files still is a great mystery to us. So I want to continue talking about this kinetic and potential energy and how we relate heat with kinetic energy and work with potential energy, position of particles. So motion, random motion of particles is heat. Relative positions, whether they're because of bonding or some kind of attraction, that's a potential energy. So we can talk about that in terms of the heating of a mole of water. So let's take a mole of water as ice, so frozen water, and we'll take that frozen water and begin to warm it up. Now, if we're going to warm it up, we have to use its heat capacities. And the heat capacities are here for liquid water, 75 joules per mole. For solid water, 37 joules per mole Kelvin. So to raise a mole of water by 1 degree, you have to put in 37 joules. That's the heat capacity of solid water. So solid ice, raise it 1 degree. I'm going to bring it up to 273 Kelvin from 243 Kelvin, a 30-degree temperature range, and I get to the melting point of the ice. What I had to do was add energy, use the heat capacity of the ice to get a temperature change. So what happened there was a temperature change of the ice, the solid. The particles are now moving more in the ice. Hasn't melted yet, but the potential and the kinetic energies of the particles have changed. They're vibrating a lot more than they did. Yes.
Can you explain what Kelvin is?
I'm sorry. Kelvin is our absolute temperature scale. We had that in the first lecture. So this temperature is in Kelvin, not Celsius. So 0 Kelvin or 0 in Celsius is 273 Kelvin. So you can go from your Celsius temperature scale to your Kelvin temperature scale by this factor of 273. 0 Celsius, add 273, you get to Kelvin. Any Celsius temperature, the degree sizes are the same. So it's just a linear factor of 273, just added on top. So the degree sizes are the same, Celsius and Kelvin. So I'm talking Kelvin temperature, frozen ice. So I've brought it from cold up to the melting point of ice. And that took some energy. It was a change in kinetic energy. Heat flowed into the system. Now I'm going to allow energy to flow into the system. It's solid ice at this point. I'm going backwards. It's solid ice here. And now I'm going to melt the ice. When I melt the ice, I'm changing the potential energy. The particles are moving away from each other in an organized way. So as they move away, move away in an organized way, that energy is being stored as potential energy in the system. They're farther apart, I'm pulling them apart. Energy is going into the system. And that's a work type of energy. It's energy flow going in, immediately converted to potential. So it's work being done. And to do that, I have to take the energy it takes to melt ice. It takes, we have a unit change there. We have to put in a, I just have 6 joules per mole to melt that ice there, a mole of ice. That heat coming in is isothermal. When ice gets to 0 degrees, all the energy that comes in at 0 is separating the particles going from solid to liquid, but there's not a temperature change. The relative random motions aren't changing. So ice melts at 0 degrees until all the ice is melted. Then the next joule that comes in starts to raise the temperature. So all these joules that come in here, this is energy at the bottom, all those joules that come in there are in melting the system. And I have to apologize. I don't know if I can keep it up there. These are kilojoules coming in to the system there. It takes like 6 kilojoules of energy to melt the ice. I think if I make that go away, hold on, I think I can use PowerPoint ink tools. I think if I put the K here, there, it'll stay there. Now I have now added my 6 kilojoules. I call that the energy of fusion. Fusion is melting. So 6 kilojoules went in, the temperature didn't change. It all went into potential energy, separating the molecules from each other. Now I'm at liquid water at 0 degrees. I go from liquid water at 0 degrees, I heat it all the way to 100 degrees C, or add my 273 to get Kelvin. I go 100 degrees up from 0 Celsius to 100 Celsius, from 273K to 373K. That temperature change is the heat capacity of water. So it takes me 75 joules to raise the temperature of 1 mole of water 1 degrees. I've got to raise it 100 degrees. So I need 100 times this much energy. So 100 times that much energy is 75 kilojoules. 100 times my 75 joules. The temperature change is 100. Heat capacity is 75 in joules. That is all random motions of the liquid water. There's a question.
Can you talk about how work is involved in this graph? Because a lot of students are asking where work is going in or out.
So the question is, how is work being done is the question. So if energy flows into a system and changes the potential energy, we call that work. So how is the work being done? You're saying, well, how did I get in there? Is there somebody in there pulling each individual particle apart? That's not what's happening. Energy is flowing in. We're calling that energy flow work because it's changing the potential energy. We're differentiating it from heat. We're saying work is being done on the system. So one way to think of it is you've got a hot plate in there. Energy is flowing into the system. Energy flow, we call it either heat or work. We call it work when the potential energy changes. We call it heat when the kinetic energy changes. So we have to look at the result of what's happening to classify it. So you can still have the hot plate there, energy going in. The energy is work because it's not changing the temperature, it's pulling the particles apart. There's no physical little demon in there doing work. So it's just a classification. Okay, energy's going in, energy's coming from a hot plate, but we're calling it work because it's changing the potential energy. So once we're up here, now we have to go to steam. So we have to have the vaporization 40 kilojoules for a mole. So I got to go from water, liquid water at 100 degrees to gaseous water at 100 degrees. That energy coming in, we're going to call work. It's going to change the energy by 40 kilojoules. So now the system has absorbed all this energy. All the way out here, I've separated 55, 60 kilojoules of energy went into the system. Some of it we're going to call kinetic. It's going to change the temperature. Some of it we're going to call potential, associate that with work. This we're going to associate with heat. This we're going to associate with work. Potential energy changes and kinetic energy changes. So let me ask you then, which is more dangerous to come in contact with at 100 degrees C or 373 K, 373 Kelvin? Steam coming out of the kettle, liquid water, putting your hand in the kettle, or a mixture of the liquid water and the steam? Think about that for a second and take a vote. Can you mute me? Okay, I'm back. Talked to a group who really were on top of it. They convinced me immediately. Ryan, let's see what the group is thinking now. We've moved towards A. That's great. I think I can go back to the PowerPoint. You've gone back to A and said it was the steam, and a lot of good discussion going on. But let me tell you, yes, I agree with the steam people. If you have hot water, it can release some of its energy and into your skin and burn you. There's no doubt about it that will happen. If you come in contact with steam, steam has that vaporization energy as well as the energy of temperature, the potential energy as well as the kinetic energy. So the steam can condense to hot water, all that energy going into your hand and burning you. And then you still have hot water on your hand. And you're going to get burned the rest of the way as you go down to cool water. Now, a couple of people in this breakout room that I was in made a very good point. It has to be the same amount. So you have to come in contact with a mole of steam, and this has to be a mole of hot water. Remember, energy is extensive. So you have to come in contact with the whole mole of steam. That is, the whole mole of steam has to condense on you to get that full energy. And that's one of the conceptual things. You can think if you open the coffee pot and the steam comes out, a little bit condenses on you and you get burned. If you stick your hand in the coffee pot, yeah, you're gonna get burned really bad because there's a lot more water. So there's a lot more energy to be transferred because of the extent of the system. There's more water and energy goes as the amount. But in general, if you have the same amount, if you're in contact with the same amount of water, the steam is dangerous. I like it. So let me just talk just briefly. We'll let you guys go, or we're so close to the end. We'll talk about human thermochemistry next time. We're running a little behind, but I can go quickly through human thermochemistry next time. Are there any questions just hanging out there that anybody would like to ask? Yes. The question is, can we see Avery? Yes, you can see Avery, but while we're looking at Avery, I know what you want. You just want the camera off me. Are there any other questions, Ryan? There's Avery. I think Avery's probably paying about as much attention as half of you guys. Does anyone else, show of hands, start the poll. Is anybody look kind of like Avery when they come to lecture? Completely sacked out. Are there any science? Are there any science questions coming up?
They want you to clarify why the answer wasn't both water and steam.
So a question came up, why not water and steam? So again, we have to go to the total amount. So if it's a mole of water, half of it's steam and half of it's water, then the steam, only half of the water has that extra vaporization energy. If you got the whole mole of water vaporized, then all of it has that extra energy. It's a good question. You're saying, well, what if I dive into the pot and swim around in the steam? It's the extent question. If it's still just one mole combined of the water and the steam, then it's the steam itself is more dangerous.
Can you talk a bit more about state versus path functions?
The question is, can I talk more about state versus path functions? And I haven't even said those words yet. So this is, let me answer. I mean, you're asking a question. Just very briefly, the energy is a state function. It depends only on the state, the initial state and the final state. Anything that happened in between, you can't tell. It's not recorded in the energy. So if you got, it's like having blinders on. You look at the system, thump, blinders go down, thump, they come back up. All you see is the change, and you didn't see how it got there. If you were watching, you might have been able to tell that work and heat were going on, but you weren't watching, so you can't. So the work and heat are dependent on the process. And you said the word path, that's process. They are properties of the process. They're the flow. But the energy, the state function, it doesn't really care, in a sense, what happened. It just knows, we just know the energy changed. So just think about it like that. If I can't see it, it didn't happen. All I know is the energy changed. That's about it for today. Sorry, we're trying to get all the technical stuff worked out. A lot of it's the machine. Ryan is right on top of it. Everything she does works. Melissa, getting you in and out of discussion groups is working great. Please, if you want to have specific people in your discussion groups, your breakout rooms, fill out that form online. Tomorrow we're going to talk about the launch of the PRISM system. We're excited about that. See you guys all tomorrow.